Hello, welcome to the first video lecture for Organic Chemistry 201. This lecture will cover Topic 1, Bonding Patterns and Structural Formulas. So, organic chemistry is concerned with the chemistry of carbon-based molecules. And in order for us to begin our study of this, we need to understand the covalent bonding patterns that carbon in the elements that we typically find in organic molecules undergo. And so the elements that we're going to be interested in today are carbon, hydrogen, nitrogen, oxygen, sulfur, phosphorus, and then the halogens, which are fluorine, chlorine, bromine, and iodine. Now, for two atoms to form a covalent bond, they need to share two electrons equally. So a covalent bond involves two electrons equally shared. So each atom that's participating in this covalent bond is going to give one electron towards it for a total of two in the bond. In order for us to know just how many covalent bonds each of these different elements can form, we need to know what their valence shell looks like and how many electrons are in that valence shell. So if we begin with carbon, carbon's valence shell is, its electron configuration is 2s2, 2p2. For that valence shell to be full, there need to be a total of 8 electrons. Right now, it only has 4. So that it means it needs 4 electrons to have a full shell. And in turn, that means it can make up to 4 covalent bonds. Now, the next most common element that we're going to encounter in our studies this semester is going to be hydrogen. Hydrogen's valence shell is 1s1. That valence shell, 1s, can only hold up to a total of 2 electrons. So that means it needs 1 more electron, and it gets that by forming 1 covalent bond. We're going to continue this process for the rest of the elements, and so for nitrogen, we see its valence shell is 2s2, 2p3. It needs 3 electrons to get its valence shell up to 8, and so it forms 3 covalent bonds. Now, moving on to oxygen, we are at 2s2, 2p4. It needs 2 electrons, and so it forms 2 covalent. Now, sulfur and phosphorus are special cases. Their valence shells are the third shell, and so for sulfur, its valence shell would be 3s2, 3p4, which is very similar to oxygen. It would like to get 2 more electrons and form 2 covalent bonds. But we'll see that there are special cases where what we'll call hybrid orbital theory, which we'll learn about in the next couple of weeks, allows sulfur to make up to 6 bonds. Again, that's a special case. Typically, we'll see it forming 2 covalent bonds, but we can also see it go so far as up to 6, with 4 being another common example. Similarly, so oxygen and sulfur are related. Similarly, phosphorus and nitrogen are related, in that phosphorus's valence shell, 3s2, 3p3, would lead us to expect that it needs 3 more electrons and would form 3 covalent bonds. But we'll see that phosphorus, like sulfur, has some special cases where it can form up to 5 bonds. And again, that's a special case, so we'll typically expect to see sulfur only form 3 bonds. Now, all of the halogens have the same valence shell, just different rows. And that's always going to be S2P5, which means that the halogens are looking to gain 1 more electron, so it needs 1 electron, and will form 1 covalent bond. Now, these bonding patterns assume that the bonds we're forming and the molecules we're producing are going to be neutral in charge. We'll see examples as we move through the semester for all of these elements where we can break this rule to form a charged intermediate. But if we break these rules, there will be a charge on that atom in the molecule. For there to be no charge on the atom, we need 4 bonds to carbon, 1 bond to each hydrogen, 3 bonds to nitrogen, 2 bonds to oxygen, 2 or more bonds for sulfur, 3 or more bonds for phosphorus, and 1 bond for each halogen. Now that we've seen the common covalent bonding patterns for the elements we're going to most frequently encounter in organic chemistry, let's take a look at a couple of the different ways that we can represent the structure of different molecules. Now, there are some very, very simple molecules, for example, methane, which are easy to represent, drawing out all atoms and all bonds. Now, if we take something that's more complex, say dodecane, for example, which has a molecular formula of C12H26, if we were to explicitly draw out every atom and every bond, it would take quite a while. We have 38 atoms to get through and almost an equal number of bonds that we need to draw. Furthermore, we can't just write C12H26, the molecular formula, since that doesn't convey any sort of information about how the different atoms are connected to each other. And so we could be, by just writing this molecular formula, we're actually representing a wide family of organic molecules known as constitutional isomers. And we like to be very specific, or as specific as possible, whenever we're representing a structure. So, two of the ways that we're gonna see 2 new ways to draw molecules. One is gonna be, and the first is gonna be called a condensed formula. A condensed formula reduces the number of bonds that we need to draw in the molecule, but still shows every atom explicitly. Let's take an example. If I start with this molecule here, you can see it takes a little bit of time to draw this out. However, we can cut this down by grouping atoms together and not showing all of the bonds explicitly. And so we'll begin with what we call our hydrocarbon fragment, this portion of the molecule here. Now, this hydrocarbon fragment is composed of 1 CH3 group and 2 CH2 groups. So we can condense each of those to its constituent atoms. So we have a CH3 group connected to a CH2 group connected to another CH2 group, which then is connected to our carboxylic acid, which is our functional group in the molecule. We can take this a step further and omit a few more bonds and simply write it as CH3, CH2, CH2, C. A little bit quicker. We can condense that even further by grouping our two CH2 groups together. Now, for our carboxylic acid functional group, the portion marked here in pink, we can condense that down, but it has to be specific to the carboxylic acid functional group. And so for the carboxylic acid functional group, C double bonded to an oxygen, single bonded to an oxygen, single bonded to a hydrogen, there are two different ways that we can condense that down. We can represent it either as COOH or CO2H. Either of these two methods for condensing the carboxylic acid functional group are perfectly acceptable and communicate the same information, which means that ultimately this molecule, which has, let's see, 7, 8, 9, 10, 11, 12, 13, 14 atoms and a myriad of bonds, can simply be represented as CH3, CH2, 2, CO2H. This condensed formula conveys the exact same information as this fully drawn out structural formula. So again, this full method is known as a structural formula, whereas our nice, tight, quick, and easy to write version would be a condensed formula. Let's take a look at one more example. Here in the second example, we have a slightly more complex molecule that introduces a few more elements into it. Here now we have an amine, a hydrocarbon group that has a halogen in it. We have a ketone functional group, and we have a hydrocarbon group with a double bond. Now, just because we've introduced new factors doesn't mean that this process will change significantly. We'll first start, as before, by condensing all of our hydrocarbon groups. So we'll leave our amine the same. Now, here we have a CH2 group. Here we have a CH with a chlorine attached. Another CH2 group. We still have our ketone. And we can condense the hydrocarbons in our double bond scenario, with the CH double bonded to a CH2. We've now just condensed each of those hydrocarbon fragments down a little bit. From there, we can begin to attack some of our other groups. Now, our amine functional group is condensed in a similar way. However, when amines are on the starting point of a molecule, we typically write their hydrogens first. So as opposed to a CH3, if this was our methyl group, we're going to have an H2N. And we have our CH2 following that. When we want to condense a halogen in with our hydrocarbon group, we write our hydrocarbon group first, CH, and we insert that halogen inside of parentheses right after it. Our next CH2 group is unchanged. We can do the same trick with our ketone functional group that we did with our halogen. We have our carbon, we put in parentheses our oxygen from the ketone, and then we continue on with our molecule, our hydrocarbon group with an alkene in it doesn't change. Finally, in our last step, we can eliminate all of the bonds connecting the different groups we have and simply write this as H2N, CH2, CH, chlorine in parentheses, CH2, C, oxygen in parentheses, CH, CH2. So this method allows us to eliminate drawing all of the bonds in and takes us from a full structural formula to a compact and easy to write condensed formula. We have condensed this structure by eliminating as many bonds as possible from being drawn. Now, because carbon and hydrogen are such ubiquitous elements in the study of organic chemistry, we've developed an even simpler shorthand which eliminates the need for drawing carbons and hydrogens in the majority of our structures. This is known as a line structure or a line formula. And line structures are by far the most common method for drawing organic molecules and drawing most molecules in general. This is the fastest and most efficient way for us to draw a compound to convey the information that we need to. Now, in a line structure, we omit all of the hydrogen atoms, and carbons are denoted as the beginning and end of a line segment. So I'm just going to come here and draw a dot above each carbon that we're going to have to represent in our line structure. And I'm going to circle the elements that have to be explicitly drawn. One of the other differences is that we do, in a line structure, explicitly show every carbon-carbon bond that's in the molecule, and we also explicitly show every carbon heteroatom bond in the molecule. Keep in mind from when we were looking over from your worksheet on bonding patterns that a heteroatom is any atom in an organic molecule that isn't carbon or hydrogen. So how then can we take the structures that we've represented here and turn them into line structures? Well, simply we begin by drawing out our carbon framework. I have 1, 2, 3, 4, 5, 6 carbon atoms in this molecule that are all connected to each other. And so I'm going to start out by just drawing, there's one carbon atom. This line represents a bond to our second. Here we go to our third, to our fourth, to our fifth, and finally to our sixth carbon atom. 1, 2, 3, 4, 5, and 6. Okay? Now we'll begin filling in the features. So between carbons 5 and 6, we see we have a double bond. And so I just put a second line here connecting 5 and 6. There's our double bond. Off of carbon 1, we have an amine. So there's our nitrogen. Let me draw that a little bigger for you. Here's our nitrogen, and we do explicitly write out the hydrogens that are attached to that heteroatom. On carbon 2, 1, 2, we have a chlorine attached. Because chlorine is not a carbon or a hydrogen, we're going to explicitly draw that out. And then finally on carbon 4, 1, 2, 3, 4, we have a ketone. So we have a double bond to an oxygen. Now, here I've taken my time in drawing it out, but you can see that when I'm in a hurry, it's actually much faster for me to draw a line structure than it is for me to do a structural formula or a condensed formula. And so these line structures are going to be the way that we represent our organic molecules most of the time. You will be asked to produce condensed formulas, and you will be asked to produce structural formulas at certain times. However, the line structure is really going to be what we're going to use the overwhelming majority of the time in this class.